Hello, welcome to today's session. Today is the week 8 of the problem solving session. And today we'll be looking into the week 9 lectures, not week 8. Week 9 lectures that were focused on water losses, what are the different kinds of water losses, what is water auditing, what are the different terms in water auditing and how they are computed and how water losses are being detected. This was the main focus of the week 9 lectures. And we'll be discussing few problems in coming under these lectures that will be helping you solve the assignment questions for that week 9. So we'll move on to the questions. I hope I'm audible. If someone could just confirm it via chat, it would be useful.
Yes, it is audible.
Thank you. We'll move on to the question discussions. Like I said the last week, I've compiled a couple of numerical problems of week 8 and week 7 also for discussion in the session that we'll be discussing towards the end of the session. So we'll go through these the first topic, that is week 9 lectures topics, and then we'll move on to the assignment questions of week 8 and week 7. Few of them, just the numericals. So here the first question is, the water lost from a water distribution network due to mismanagement of assets and resources rather than real leaks is denoted as apparent losses, non-physical losses, commercial losses, or all of the above. You can type in your answers in the chat box. Okay, so we'll move to the answers. So water losses mainly are of two categories. One is the real losses or physical losses. The other one is apparent losses or non-physical losses. Now, apparent losses or non-physical losses are also named as management losses or commercial losses. Now, let's see what these are. Real losses or physical losses are those losses which are occurring physically by all means, like when there's leakages in the pipe network, or where when the pipe bursts, the water loss because of such reasons, and when there's overflow in the system components also are called real losses or physical losses. Now, apparent losses or non-physical losses are actually happening physically, but it is majorly the reason why these losses are happening. Even if there are water bursts or water overflows, or sometimes when there are theft of water, or when there are faulty meters, when the meter connections or the metering system is faulty, then such losses occurring are called apparent losses or non-physical losses. So this is actually occurring as a result of mismanagement of the infrastructure management team, or the systems they are systems that they are using, which is not working efficiently. So such losses as a result of these mismanagement or problems in the components of this distribution network that are meant to account for water, such losses are called apparent losses or non-physical losses. So in that recording or data handling errors, metering inaccuracies, when water is being stolen, or there are unauthorized consumptions, these kinds of losses are coming under apparent losses or non-physical losses. So the answer for this question would be all of the above, because it is the water loss from a water distribution network due to mismanagement of assets. So that is called apparent loss, or the other name for it is non-physical losses, or it is also called commercial losses or management losses. So the answer for this question would be option D. So moving on to the second question. Seepage through a reservoir or tank walls and overflow due to flow to wall failure are accounted as. I'm sure you'll be able to answer this question because we have just seen what the two types of losses are. Options are real losses, physical losses, management losses, commercial losses, or none of the above. Alex said, oh yeah, I'm getting an answer. Sangamitra said A. Alex, you can also just type in your answer, right? So, like we had seen, these are occurring because of overflow due to float valve failures. The valves, as a result of valve failure, there is water loss happening, or when the seepage is occurring through these tanks, then it is called, these are actual physical losses, and they're called real losses of physical losses. So here you can see some of the examples: burst pipes, leaking joints, fittings, fittings that are resulting in leakage, service pipes that are resulting in leakage, connections. If there are connections are improper, then the leakage is occurring as a result of it. Then when the reservoir walls are seepage is occurring due to improper lining or whatever reason from the reservoir walls, or float wall failures, overflow occurring due to float wall failures, all the water loss occurring as a result of such these reasons come under real losses or physical loss. Now, before we move on to the third question, I would like to discuss some terms that is coming when we have to conduct a water audit. Water audit is nothing but for whatever water that is being input into a distribution network, we have to be able to compute how much of water is being sent into the distribution network, how much of water is being effectively used, how much of water losses are occurring. All these have to be calculated. And for the purpose of calculation, there's water auditing occurring. And with respect to water auditing, there are some important terms that we have to be familiar with. And these terms are what you can see in this slide. So some of the major components of water balance calculation. Water auditing is mainly occurring by using the water balance method, which is how much water is going inside the input minus output. If it is giving a little bit of difference in the storage, then that is actually resulting in that amount of water that is being lost without being used. So it is based on this water balance principle that water auditing is happening. And the major components of water balance calculation is, first is the system input volume. System input volume is nothing but the amount of water that is going into the distribution network, how much water is going as an input. And this input computed is the annual volume of water that is being sent into the distribution system. So that is the first term that we have to be familiar with, system input volume, or in short form, it is used as SIV. Now the next one is the authorized consumption. Authorized consumption is again this annual volume, that is the system input volume, which is metered as well as unmetered. Now, metered water is the water we are actually consuming. What is the amount of water? What is the meter connection? What value the meter connection is giving us? That amount of water, as well as sometimes due to the fault in the meter connections, there might be extra water going. So, all those water is coming under the authorized consumption. And not only that, it will also include the water that is used up for firefighting, that is water that is used for maybe cleaning the sewer pipes and all, water that is used in public fountains, water that is used for watering of public gardens. All of these come under authorized consumption. Now, the third component is water losses. It is also called unaccounted for water. Now, we'll go further into unaccounted for water, but again, this is one important term that you have to keep in mind. Water losses or unaccounted for water. Now, water losses, we just now saw, there are losses occurring as a result of various factors like leaks, bursts, overflow, due to meter connection faults, due to theft of water. All these are coming under water losses. Now, there is another term called non-revenue water. This non-revenue water is the annual water volume of the total losses and unbilled authorized consumption. In order to understand what non-revenue water is in a more better way, we'll go on to this pictorial representation of this components of water balance. So here we saw the system input volume is this water that is supplied into the distribution network. Now the system input volume, it will go as authorized consumption, as well as some of the amount will be lost as water losses. Now under water losses, there are two types of losses. One is the apparent loss and one is the real loss. Now under the authorized consumption is nothing but we have some set of consumers that we know are going to be at the end of receiving this water or utilizing this water. We are aware of that, and they are supposed to be paying the water utility department for the water they are using. Authorized customers are such customers, and they are using this authorized consumption. In that, some of the water is being billed. Most of the water is being billed, but there is also an amount of water that is being unbilled because of the problems in the metering system or whatever reasons. Now we came into here for looking at what non-revenue water is. Non-revenue water is nothing but the sum of all these losses plus the unbilled authorized consumption is equal to the non-revenue water. Or when we say that this amount of water is non-revenue water, it is including the apparent losses, the real losses, and unbilled authorized consumption. So once more, going through this entire network, the system input volume comprises of authorized consumption and water losses. In water losses, there are two categories of losses, the apparent losses and the real losses. In authorized consumption, there are two categories of authorized consumption. One is the unbilled authorized consumption, and another is the billed authorized consumption. And in that, what we call as non-revenue water is the total of these water losses plus the unbilled authorized consumption is called non-revenue water. So non-revenue water, or NRW, is an important term that we have to keep in mind. Again, all the following questions are going to be in one way related to, it will have a lot of questions using this non-revenue water and all the losses, unbilled authorized consumption, billed authorized consumption, etc. So that was a pictorial representation. Here they have made a chart of how this can be, the same thing can be put. The system input volume is comprising of authorized consumption plus the water losses. In authorized consumption, there is billed authorized as well as unbilled authorized. Now, billed authorized itself has some amount of water, that is billed meter consumption and billed unmetered consumption. Now, unbilled authorized consumption itself is consist of unbilled metered consumption and unbilled unmetered consumption. Apparent losses and real losses, we looked into it. So unbilled authorized consumption plus apparent losses plus real losses is giving us non-revenue water. Now there are performance indicators that are used for representing these water losses, or how much of water system input volume, or what water is coming under authorized, what is not coming under authorized, and all that. So some performance indicators are, one of them is what we see now. So now the non-revenue water. Another is the unaccounted for water. Again, unaccounted for water, we had seen in the earlier slides. Unaccounted for water is nothing but all the water losses. So the sum of the real losses plus apparent losses is what is unaccounted for water. So here also they are saying, how can we find the unaccounted for water? Suppose we are given the system input volume and the authorized consumption. The water losses are there, authorized consumption is there, system input volume is there. So finding the difference of the system input volume and the authorized consumption is going to give us the amount of the water losses, total water losses. UFW can be found out like that. Now, non-revenue water can be found out by finding the difference between the system input volume and the billed authorized consumption. So we are again going through this slide once again. Non-revenue water is the sum of unbilled authorized consumption, apparent losses, real losses, and system input volume minus this billed authorized consumption will give us the non-revenue water, and system input volume minus the authorized consumption will give us the water losses, or this water losses, another term that is used for that is unaccounted for water. Now, other performance indicators are current annual real losses. This is nothing but if the total real losses in the system is called as current annual real losses also. So now there are some real losses that is unavoidable. Suppose there are small leakages. These leakages, in order to repair them, it might be even more costlier than letting the leak happen. So in under such situations, the repairs and all are not done, and the water leakages continue to happen. So such leakages or such water losses are coming under unavoidable annual real losses or UARL. Now, UARL can be computed using these two formulas. I'll be repeating the slides when the numericals relating to this part comes up. But again, just to go through all the formula, UARL, when it is to be produced as letters per day, can be computed using this formula, where LM is the length of the mains, NS is the number of service connections, LP is the length of the pipes underground, and P is the average pressure. Now, suppose if you want UARL in meter cube per year, you can calculate using the same formula but with different constants. Now, the other performance indicator is infrastructure leakage index. Infrastructure leakage index is nothing but the ratio of the CARL, that is the current annual real losses, and UARL will give us the infrastructure leakage index, and its ideal value should be equal to 1. So if there is no problem with the infrastructure or management, the value should be equal to 1, and that is called the infrastructure leakage index. Moving on to the question. So we learned about what is UFW, NRW, non-revenue water, UARL, which is unavoidable real losses, CARL, current annual real losses, and infrastructure leakage index. So this question is relating to these terms that we studied. Here they've given 3 statements. First statement, in a typical water utility, UFW, unaccounted for water, is a component of NRW. Billed metered consumption is not a component of NRW. ILI, or infrastructure leakage index of a utility, can be estimated if either its UFW or NRW is known. Which out of the following statements are true or false? If all the statements are true, you can choose option A. If only the statement 3 is true, you can choose option B. If first and 3 statements are true, you can choose option C, and D for if statements 1 and 2 are true. I know it's a lot of information to process. Okay, so we'll move on to the answer. So the answer for this question is option D, because 1 and 2 are true. So in a typical water utility, UFW is a component of NRW. Now, why is it true? We'll just go back on into the slides. We had seen here, what is UFW? It is unaccounted for water, and unaccounted for water by definition is all the system input volume minus the authorized consumption. That is, the water losses, total water losses are actually the unaccounted for water. Now, unaccounted for water is also a part of non-revenue water, which is what the statement 1 is about. So in a typical water utility, UFW is a component of NRW. That statement is true. Now, second statement is saying that billed metered consumption is not a component of NRW. Let's again go back. Here, billed metered connection is a component of the revenue water. It is not a component of NRW. So that statement is also true. Third statement is infrastructure leakage index can be estimated if UFW or NRW is known, which is false. For estimating ILI, we need to know the current annual real losses CARL and unavoidable annual real losses, which is UARL. So ratio of CARL by UARL is what is giving us ILI. So we cannot estimate ILI with UFW or NRW, but instead estimation of that is done using CARL and UARL. So the statements 1 and 2 are true. Hence, the option D is the correct answer. UFW is a component of NRW, as NRW is including all the losses. Unmetered consumption is not a component of billed unmetered consumption is a component of the revenue water and not non-revenue water. ILI can be computed using CARL and UARL. Now moving on to the fourth question. The real losses in a water distribution network usually increases with Sangamitra has given the answer C. I mean option C is the correct answer. Alex Kuti also said it C. Okay, let's move to the answer. Mujahid, you can also type in your answers in the chat box. So some of the factors that are influencing real water losses are the following. The percentage of time per year during which the network is pressurized. Network pressurizing is nothing but where what all time is water going through the pipe and being supplied. That is called, that is when you say that the network is pressurized on all the time when the water is going through the pipelines. So one of the factors influencing is the percentage of time per year during which the network is pressurized. Again, the average operating pressure, the number of service connections, then number of joints, valves, and gauges, length of the mains. All this we are using it for calculating the UARN, if you remember from the earlier slide. Then the age of the material or the frequency of leaks and bursts. Then type of soil and ground conditions. So these are some of the factors that are influencing real water losses. So why is it 3? The option C. So increasing the number of consumer service connections is one reason for which real water losses can increase. Another reason is increasing the number of joints, valves, and gauges. Again, increasing the average operating pressure of the system is also a reason for the real water losses to increase. So the option C will be the correct answer for this question. Moving on to the fifth question. Unauthorized consumption plus metering and billing inaccuracies in a water distribution network is equal to what? Real losses, non-revenue water, unaccounted for water, or apparent loss? Jahid said it's B. So we had studied about system input volume comprising of authorized consumption and water losses. In water losses, we saw about real losses and apparent losses. And authorized consumption, we read about billed consumption and unbilled consumption. Here, what they're talking about is unauthorized consumption plus metering and billing inaccuracies. What kind of losses? So, what component of water balancing does this category belong to? Okay, I'll move on to the answer. So, here, if you see in the apparent losses, the categories of apparent losses are inaccuracies in the meter readings, the input output, and unauthorized consumption. Unauthorized consumption is nothing but water that is being consumed without the knowledge of the authorities, which is illegal usage of water or stealing water is coming under unauthorized consumption. And also metering inaccuracies is also an apparent loss. So the answer for this question is apparent loss. Unauthorized consumption plus metering and billing inaccuracies are coming under apparent losses. Moving on to the next question. The core component of non-revenue water is. I know you should have got an idea of what non-revenue water is and what the other components are. So I believe all of you will be able to give this answer. What does non-revenue water comprise of? Okay, Alexis given D. Okay, Mujahid has also said it's D. So we saw here what non-revenue water is. All real losses, apparent losses, and unbilled authorized consumption. So all of the above is the answer. It comprises of all the three components in the water balancing calculation. Now moving on to the next question. Which of these methods can assess the volume of leakage in a water distribution network without pinpointing its location? So this is about how the water leakage is detected. These are some of the techniques they have told here. The question asked here is, how can you assess the volume of leakage without actually knowing the location of the leakage? Okay, I'll move on to the answer. So the answer for this is minimum night flow analysis. Minimum night flow analysis is nothing but the leakage is detected by, even if we don't know the location where the leakage is happening, the amount of water leakage can be computed through this minimum night flow analysis. So what happens in minimum night flow analysis is, for a DMA, I'll explain what DMA is later. In minimum night flow analysis, the time period between 2 a.m. and 4 a.m. is one period of time when water usage by the users are very less. So if during this particular time, if the water use is very high, then that water usage is considered as a result of leakage. So it is in this principle that minimum night flow analysis works. DMA, under minimum night flow analysis, one important equation or relationship is the pressure leak relationship suggested by Lambert, which is given by L1 by L0 is equal to P1 by P0, the whole power n, where L is indicating the leakages, P is the pressure in the pipes, and n is the exponential coefficient, exponential constant, which is varying from 0.5 to 1.5 when the leakage considered as a fixed area leakage path. If the leakage considered is in a variable leakage path, then it becomes 1.5. So this is one important relation when it comes to minimum night flow analysis. Now we see a term called DMA over here. DMA is nothing but when the entire distribution network is zoned or demarcated into areas or zones based on certain conditions, then it is called a district metered area. So in a particular district metered area, this 2 to 4 p.m. Water flow is analyzed, and if it is seen as is unusually high usage of water during 2 to 4, then it is considered as that amount of water is calculated as water leakage water and not actual consumed water. So here the question was about assessing volume of leakage without pinpoint its location. So we don't know where the leakage is happening, but we can compute the volume of water that is being gone as a result of leakage. So the answer for this question is option B, minimum night flow analysis. So in the other two techniques, what is happening is this is for detecting where the leakage is happening. Ground microphone and tracer gas techniques are two methods which is you employed for finding out the point of leakage. The next question, which of the following is a remote mode of leak detection and quantification? So again, these are some methods for methods to understand where leakage is happening or leakage detection. Which out of this is a remote mode of leak detection, which means that it is not actually going into the point of leakage, but remotely we can understand where the point of leakage is occurring at. Okay, so we'll move on to the answer. So these are some different techniques, few of the techniques for leak detection and quantification, some advanced methods. Infrared thermography, that is making use of infrared images to understand where leakage is occurring and where leakage is not occurring. Then there's ground penetrating radar, again making use of electromagnetic waves and transmitting into this ground and understanding the leak location. Then there are leak detecting robots. One of the example is smart wall is actually sending some robotic devices through the pipes or through the ground to understand where the point of leakage is. Same is the case with some micro electromechanical devices like sensors, which is actually helping us detect the leak. And data science and analysis based software is also making use of artificial intelligence and other statistical approaches and data analysis techniques to understand where the leakage is occurring. So in this, the ground penetrating radar and the leakage detecting robots and micro electromechanical devices are actually being placed or close to the leakage system or on the pipelines for understanding the leakage. So they are not remote techniques. Instead, infrared thermography is one. uh, Infrared thermography and ground penetrating radar is one remote method of did I say ground penetrating radar is not a remote? Okay, the leakage detecting robots and wireless electromechanical devices. The third and the fourth one are not remote methods. They are actually employing some devices near to this leakage system to understand where the leakage is. But infrared thermography, ground penetrating radar, and data sensing techniques are remote processes. So the answer for this is ground penetrating radar technique. It is a remote mode of leak detection and quantification. There are also other techniques like the ground microphone technique and tracer gas technique. It is available in the lectures. You should also go through that. Now we are coming into a numerical that is based on the NFW non-revenue. What is not a numerical, a simple computation. So here an urban water utility is pumping an average of 600 million liters per day of treated water into a water distribution network. The authorized consumption is 525 million liters per day. It's and revenue from the billed metered connection is 475 million liters per day. So here the system input volume is given, the authorized consumption is given, the billed meter connection consumption is given. We are supposed to be calculating the approximate value of the NRW, non-revenue water, and the unaccounted for water respectively. I think I can give you a few minutes of time to go through this problem. These are based on whatever components that we had studied, simple mathematical computations. You can also, I'll help you with this slide that is actually giving us a relation between the UFW, NRW, SIV, etc. So here if you see, the UFW is equal to system input volume minus the billed authorized consumption minus the unbilled authorized consumption. That is authorized consumption. Altogether authorized consumption, there is billed also, unbilled also. So the system input volume minus the billed authorized consumption minus the unbilled authorized consumption will give us UFW, or we can actually take the sum of the real losses and the apparent losses if that value is given. The percentage can be computed by finding these two value and dividing it by the SIV. Similarly, NRW is giving us the difference between the billed authorized SIV, that is the system input volume, and the billed authorized consumption. Or we can find the sum of the unaccounted for water, that is the two losses plus the unbilled authorized consumption will also give us NRW, or RL plus AL, which is nothing but the UFW plus UAC will give us the NRW. Again, this value divided into 100 divided by the SIV will give us the percentage of this NRW. So here the values that are given are these: 600 million liters per day of treated water into the water distribution network. What is that? Then they have given authorized consumption value. They have also given the billed meter consumption value. You're supposed to find out the NRW and the UFW. Please try to do this.
Will you please show the question?
Yes, sure. Zahid has given the answer D. Sanghamitra, you also try and wait for you to complete. Okay, Alex has also given us an option. Okay. So the option you've given here is D. Let's just see into the calculation. The system input volume here is given as 600 milliliters per day. Authorized consumption given is 525 milliliters per day. So unaccounted for water, we can get from this UFW, which is equal to 600 minus 525, 75 milliliters per day. That divided by SIV is going to give us 12.5%, is almost equal to 13%. So percentage of UFW is equal to 13%. Now, in order to get the non-revenue water, the system input volume minus a billed authorized consumption, which is nothing but 600 minus 475, which is given in the question. Billed metered connection is giving us 125 milliliters per day. That again divided by the system input volume, which is 600, is giving us 20.83%, nothing but 21%. So all of you have been giving the right answer. So the correct option for this question is option B. Moving on to the next question. This question is about the Lambert equation, the minimum night flow analysis. So what they've given here is leak flow rate in the water transmission line under a pressure of 3 bar is estimated as 12 meter cube per hour. Now you're supposed to determine the leak flow rate when the pressure is increased to 4.5 bar pressure using the Lambert's equation. So I had told you about the Lambert's equation, which is given at the bottom of the slide here. L1 by L naught is equal to P1 by P naught, the whole power n. So you have to compute. I mean, this is a very simple formula. You just need there is one leak flow rate provided, two pressures provided. Here the n value is considered as 0.5 if it is a fixed area leakage path and 1.5 if it is a variable leakage path. So you can consider the fixed area leakage path n value, which is equal to 0.5, and compute what is the leakage leak flow rate when the pressure is increased to 4.5 bar pressure. Using that simple formula, which is L1 by L naught equal to P1 by P naught the whole power n. N is equal to 0.5 because they have said a fixed area leakage path is being used. Okay, so Sanghamitra has given an answer. If Alex and Mujahid are doing it, I'll wait for a couple of more minutes and then we can move on to the solution. Either side it's 29.32. Alex, do you have an answer yet? Or should I move on to the solution? Okay. So, like I said, the formula is L1 by L0 is equal to P1 by P0. Direct calculation, the correct answer is 14.7. I think Sangamitra had given that answer, I believe. Yeah. So here they have given us under 3 bar pressure, the leak flow rate is 12 meter cube. That is L0 and P0 is given 12 meter cube and 3 respectively. They have also given the pressure P1 is equal to 4.5. You are supposed to be calculating L1. N is equal to 0.5. So using this computation, L1 will be multiplying L0 into P1 by P0. P1 is 4.5, P0 is 3, L0 is 12, the whole power 0.5. The answer is going to be 14.7. So that is about this Lambert relationship between pressure and leak flow. Now again, this is about a numerical related to the loss. Here they have given the apparent loss estimated from a faulty bulk meter is 15 kiloliters per day. We are supposed to compute the inaccurate reading of the faulty meter corresponding to the actual water flow of 1 kiloliter if it is recording 4,500 kiloliters of cumulative monthly flow. So what is the total reading? The 4,500 kiloliters of water is what is being recorded in the meter for 30 days. We have been given the apparent loss per day, which is 15 kiloliters per day. And they have said that the meter is faulty and that the faulty meter is corresponding to the actual flow. That is inaccurate reading. We have to find out how is the reading inaccurate. What is the inaccurate reading value that is shown in the meter? If the correct reading for 1 kiloliter of water that is being flowed. We have been given the total meter reading of the faulty meter. We have been given the apparent loss per day. From that, we have to calculate what is the meter reading and find out for 1 kiloliter per day, what is the meter faulty meter, what reading is the faulty meter giving us. This it's a pretty simple numerical, but I think we just go through the solution. So here they have said the apparent loss, like I said, 15 kiloliters per day. The actual water flow of 1 kilo for an actual flow of 1 kiloliter, what is this faulty meter reading giving us? Because it is faulty, it is not giving us the actual meter reading. Instead of the actual meter reading, it is showing 1 kiloliters when actually 1 kiloliter is not the consumption that is happening because the meter is faulty. So, so in the end of 30 days, it is recording 4,500 kiloliters of water. So from apparent loss per month, we can compute it as 15 kiloliters into the 30 days. We are getting a total loss of 450 kiloliters. Now meter display for that month is 4,500 plus the apparent loss, 4,950 kiloliters of water is actually being consumed. But the meter is only showing 4,500 because it is showing a faulty reading. So if you divide this 4,500 by 4,950, you will get that the actual meter reading is 0.91 kiloliters. So it should actually show only 0.91 kiloliters, but instead of that, it is showing 1 kiloliter because it is a faulty meter. So this is one type of question again that can come apart from the percentage of UFW and RW and the Lamberts. What is the faulty meter reading? So in order to get that, we get the total amount of total meter reading that is shown in the display. If we have the losses of water separately, we can add it and find out the actual water. What is the actual water reading that has to come in the meter? Divide the faulty reading by the actual reading and get the actual meter reading of the faulty meter. Okay, so this is a bunch of questions that is based on UARL. We had seen that UARL, what is UARL, which is unavoidable annual real losses. ILI, which is infrastructure leakage index. So based on this, there is another numerical. Yeah, they're saying that a newly built water distribution network with 1,907.95 service connections, total pipe length is 1267 kilometers, and underground service pipe is 5035 kilometers, delivers system input volume of 120 million liters per day of water. The first question, 13th question is, if the utility desires the UARL to be 3% of the supplied volume, what is the volume of water lost per year? So we had seen that unavoidable annual real losses UARL is computed using these two formulas. You can actually take down these two formulas and compute what is UARL. Because the main length, number of service connections, and total length of underground pipes is given. So you will have to use this formula for computing. First, you have to compute what is UARL. I think UARL is given. UARL is given. No, sorry. UARL is to be 3% of the supplied volume. This you can calculate for whatever data you have. You have the system input volume. What it has to be 3% of the supplied volume. Determine the volume of water lost per year in million liters per year. This you don't need the formula. You can just calculate it from the SIV and the UARL. Maybe you can give it a shot and let me know the answer. I'll be waiting for your answers. In case you want me to go forward, just let me know. I'm in the chat box. You have to be, yes, the answers will be correct, but also, yeah, correct. I was about to say the thing. You have to always mention the unit because here mentioning the unit is one important thing. Sangamitra, were you able to compute the answer for question 30?
Yes, I'm doing.
Okay. The remaining of you can actually go on to the second question, question number 14. They're asking us to calculate the average pressure required to be maintained in the distribution network to ensure a UAR of 3%. So we calculated the UAR of 3% and supplied volume. So you can make use of this formula. This formula to compute the UARL. If you can take down this formula and then we'll go back to the question. Or yeah, this is the answers for all the 5 questions. You can go back to the question. The number of service connections is 19,795. 5,035 is the length of the main pipe. Sorry, underground pipe, and 1,267 is the length of the main pipe. You're supposed to find the average operating pressure. I'll write down here probably. So using this formula, you need to find out the average operating pressure. These are the data that has been provided. Service connections, length of the LM main lengths and underground pipes length. Use the UARL value, which is 1314 that you have got, to find out what is the average operating pressure. This is nothing but P. Sangamitra, were you able to get the answer for the first question, 13th question?
Yes.
Okay. So you can move on to the 14th question.
Yes.
This is this formula. Yeah, Alex has given an answer. Wait for the rest of you. Ms. Mujahid and Sangamitra, are you trying? Yeah, if you finished the 14th question, you can go to the 15th question. So I think Alex is, it's because maybe you might have used the wrong formula, probably why you're getting this answer. There's one for liters per day and one for meter cube per year. We got the answer as 1314 million liters per year. So we have to actually use the formula corresponding to that. Liters per day cannot be used. We have to use the second formula, meter cube per year. For that, you will have to actually convert the million liters to meter cube and then use the second formula. Probably you will get the answer. Mujahid, if you go to the third question, which is to compute ILI. So in that, they're giving us the 1 year of operation is estimated as 2076 million liters per year, which is called the current annual real loss. So real loss from the system for 1 year is 2076 million liters. You're supposed to calculate ILI. You know what UARL is. Please move on to doing that question. The remaining of you, 2076 is CARL, so take note of that value. Remaining of you can use the formula here and do the 14th question and then move on to the 15th question. Alex, you can try converting it to meter cube per year and using this formula and doing it once again. So your answer is correct. Just 1.6 Mujahid. Yes, Sangamitra, your answer is right. It's 21.9. You can do the 15th question. If CARL is 2076 milliliters per year, what will be the ILI? Okay, so that was about these three questions. So first, they have given us the water supplied per day, which is the system input volume, is when you actually multiply it with the annual total volume is system input volume. So you have to multiply it with 365 days. You will get a total of 43,800 milliliters is the system input volume. They have said UARL is 3% of the supplied volume. So you will take a percentage of that, you will get 1314 million liters per year. Now, when you convert that to meter cube per year, we can use the second formula that is given over here, which is 6.57 into the length of the main plus 0.292 into the number of service connection plus 9.132 into the length of the pipes underground into the average operating pressure. We are supposed to find the average operating pressure in the second 14th question, and that can be found out because we have the UARL value in meter cube per year, which is equal to 21.9 meter. After that, Carl has been given, which is the current annual real loss, which is 2076. We also know that 1314 is the UARL. So CARL by UARL will give us the infrastructure leakage index, which is 1.58. So this is another problem that is making use of simple formulas, and also something that you have to be aware of is the units in this. As in all the problems that is coming in water supply engineering, unit conversion is an important thing. So we have to always focus, be careful of that. Now, the last class I had told that we had discussed some of the assignment questions since the assignment solutions are not yet come. So I have just solved the few numericals of the week 8 assignment 8. So we'll move on to those questions. The question number 11, which was about this pipe. I guess you'll all have the answers to it. If you have, you can just cross check with the answers. So here they have given 3 pipes of length 800, 500, and 400 meters, and diameter 500, 400, and 300 millimeters are connected in series, and they're supposed to be replaced by a single pipe of length 1700 meters. We are supposed to find the diameter of the equivalent pipe in mm. I will not, yeah. Yes. So the answer is option C. So the solution goes like using this formula, LE by D to the power 5. We are supposed to find D. We have been given LE, which is 1700, and the lengths of the individual pipes and diameter of the pipes in millimeters. So converting it into meters, you will put it directly in this formula and you will get it as 0.372 meters or 372 millimeters. Now the next question is determining okay. So the next question was about finding out the head loss, and I wasn't getting an answer for that, which is coming in the range of this question. So where all of you getting the answer for that question, which is actually asking for the head loss? The question asked is using a Darcy-Weisbach factor of f.025 and pipe velocity 3.5 meter per second. They're asking you to calculate the head loss, and the answer that is obtained is given here is 2.85 meters. Were all of you able to get that answer, or were you getting a different answer? Because I wasn't getting the correct answer, I was getting a different answer, so I just wanted a clarification on that too. Sangamidra, Mujahid, Alex, anybody?
So is it FL V square by 2GD? And
Yes.
if
Yes.
we use it, I got 71.33 like
right,
that.
right. Even I was getting 71.33. Did Mujahid and Alex also do the question? Or maybe you can just try it now. Were you able to get the answer 2.85 meters by any chance? Okay, so since that question is not something that I'm getting an answer note, I'm not putting it in the slide, but I can just say that the answer that I got was 71.33. I'm I believe. Okay, so you haven't tried it out yet. Maybe okay, just try it out, and I mean, if you're getting the answer that is told in the question number 12, maybe I'll just ask in the next session, or possibly if the assignment solutions are coming, we'll clarify then. I'm not putting it on the slide because I haven't got the correct answers. So moving to the next question, which is this. Here they have asked to calculate the the flow in Q1 in this segment of the network. The correct answer is A. I hope all of you got the answer. I'll just explain how you can get the answer. So you getting the minus and the plus values are indicating if the flow is happening in the clockwise or anti-clockwise direction. So in the clockwise direction, if the flow is in the clockwise direction, then you will get a positive magnitude, and if the flow is in the anti-clockwise direction, you will get a negative value or negative indication, that is actually indicating the flow is in the anti-clockwise direction. So here if you see, the input is equal to the output. So 120 liters per second of water is entering, 90 liters is going through this segment, 30 liters is going through. Let's not focus on the flow direction right now. We'll just compute the magnitude that is going into each segment. So 90 plus 30 is giving 120. Now here we see that 40 liters of water is going out. So from 90, if 40 is going, 50 liters per second of water is going into this two segments. And in this two segments, 30 is going through this segment, 20 is going through this segment. If you come here, 80 liters per second of water is going out. So if 20 liters is being if 20 liters per second is going into this 80 liters per second, remaining obviously will be here, will be 60 over here. Now since the direction over here is given as anti-clockwise, the flow is occurring in an anti-clockwise direction, the 60 liters is equal to minus 60 liters per second. So that is why the answer A. Correct. Mujahid, that's right. Also, but then since the values over here is given with negative and positive, and since arrows have been given in this network, it is important that you put a plus or minus sign based on whether the direction of the arrow. If it is in anti-clockwise direction, it will be minus. If it is in a clockwise direction, it will be a plus. So that is how this problem is done.
Can you solve it? Actually, you proceeded in clockwise direction from first point to second point. But
No,
if we proceed in anti-clockwise direction from towards first point, as naming is not done, so I'm saying like this.
No, instead of
yes.
naming, they have given us the direction, right? Already they
Yes.
have given us the direction. So
Yes, actually,
just go by that.
Okay, oh no, 120 liter per second is coming, then 30 liter per second if we consider that branch.
Yes.
So in that joint, 130
Okay.
liter per second is coming and another 30 liter per second is coming. So
No.
accordingly,
Okay. What I did was this 120 is being separated into 90 and 30.
yes,
Okay. Then I stopped there and I focused on this 90.
yes,
90 liters per second, 40 is going out.
yes,
And from the 90 liters per second, what is remaining? 50 is remaining. That 50, 30 of that 50 is going into this segment, 20 of that 50 is going into this segment. Now this 20 liters per second is going out, and remaining what is left, 60 is there. 60 is being contributed by this Q1 segment.
Yes, but as you concentrated after 120, you concentrated that 30 liter per second. can we concentrate 30 liter instead of 90? Can you concentrate 30 liter per second? This line.
Okay, say suppose if 30 liter per second of water is going to this Q1, because 30 is going in this direction, and 130 is coming also coming in that direction. So if this node, if you check, the total amount of water here will be 60.
Yes.
One from top and one from this diagonal section, and all of that water will go here into Q1
Yes.
60.
And already direction is given, so we will put just minus 60. Already we got
Yes,
30 plus 30,
yes,
60.
yes,
So direction is given.
yes. So first you calculate the magnitude of water that is going into each segment, and then depending on the direction, just put the minus or plus.
Yes.
Okay. So the next 14th question was this. The previous one was the 13th question. This is the 14th question. In that, they have given the diameter of the horizontal pipe carrying water at a rate of 0.25 meter cube per second, and it is reducing to 600 mm. It is reducing from 600 mm to 450 mm. We are supposed to calculate the head loss. Now here, the head loss that is being calculated is the minor loss, the loss that is happening due to contraction of the pipe. They're given the coefficient of contraction as 0.75. So we have to use this formula, K into V square by 2G. And particularly, we have to find out the velocity of the horizontal pipe. The second segment, that is the reduced segment's velocity, is what we have to consider when contraction is happening. So using this, directly putting into this formula, we know the diameter of the bigger pipe. The contracted pipe is D2. From that, so the flow is 0.25 meter cube per second. D1 is 600 mm. D2 is 450 mm. The coefficient is 0.75. From the discharge value and the area value. Area we can calculate from this diameter, and Q is given. We can find out what the velocity is, V2. V2 will get us 1.573, and then directly putting it in the formula, 0.75 into V2 square by 2G, we'll get an answer which is 0.0945 meter. I hope this is the answer that all of you have got. Sangamitra, I hope you got this. You were able to solve this. Was this the answer that you also got?
Yes, actually, I did a mistake while solving the assignment.
Okay. All right. So you can refer to the slides in that they have given for contraction, for expansion, when it is entering, when it is exiting, what are the different kinds of velocities that you have to take into consideration.
Yes.
Okay. Now moving on to the 15th question. Here they are asking us to find what kind of flow it is by giving the nature of the flow. 200 mm diameter pipe having velocity as 1.85 meter per second. The viscosity is given and the density is given. So we have to find what is the kind of flow over here. So this is, in this problem, what we are supposed to do is we are supposed to find the Reynolds number. If you find the Reynolds number is less than 2000, it is laminar flow. If it is greater than 4000, it is turbulent flow. If it is coming a value between 2000 and 4000, it is a transitional flow. And if you try solving and there are no enough values, we can choose the option D. So here we have been given the diameter, which is 0.2 meters, velocity, viscosity, dynamic viscosity, and density. Direct substitution in the formula rho Vd by mu, we'll get the answer 3,24,561, which is actually a value that is greater than 4,000. So hence the option B will be the correct answer because the Reynolds value is greater than 4,000. Were you able to solve this, Sangamitra?
Yes, I got that answer.
Okay. Cool. Now we'll go to the assignment 7, few problems. Again, here This problem is asking us to find the chlorine concentration if for a disinfection of 4.5 milliliters of water treated in a tank of volume 12 meter cube, and the CT value has been given. So we had done a similar problem in the problem solving session also. So if the CT value is given, the flow rate is given, volume is given, we can find the contact time by dividing the volume of the water by the discharge, and we are getting 3.84 minutes. That is after converting the value from days. I haven't done that step here, although we are getting in the value in days, we can convert it to minutes because that's what is required in this question. After that, chlorine dose can be obtained by dividing the CT value by this contact type, which is 57 divided by 3.84, giving us 14.84 milligram per liter, which is 15 milligram per liter. So this is how the 11th question in the assignment 7 is done. Now moving on to the 12th question. In the 12th question, they have asked us, they have given that in a gravity thickening unit, 50 meter cube of sludge is produced from the water treatment plant daily. Initial solid content is 2.2%, specific gravity is 1.1. Sludge is thickened to 40% of solid content weight by it using a gravity thickener unit. They are asking us to find the dry weight of the solids produced and also the weight of the thickened sludge coming out from the gravity thickener. So in this problem, the volume of the sludge given is 50 meter cube per day. 2.2% is the percentage of the initial solid content. So since the volume of sludge is given, we'll take 2.2% is the volume of the solids to the volume of the sludge, which is nothing but 0.022 volume of solids by volume of sludge. Now, in order to find the volume of the solids, we will multiply this value with the volume of the sludge, and it will give us 1.1 meter cube of solids per day. Now, specific gravity is given 1.1. We know that the specific gravity of specific gravity of by definition is the density of the solid by density of water. So multiplying 1.1 with 1000, we'll get the density of solid cells 1100. Now, when we multiply the density into the volume of the solids, we will get the weight of the solids. So 1100 into 1.1, you will get 1210 kilograms of solids per day. That was the first question. Dry weights of the solids produced in 1 day. Now, the weight of the thickened sludge coming out of the gravity thickener was the next question. So we know the weight of the solids is 1210 kilogram per day. They have given the thickened sludge coming out is 14% of solids weight by what? That is weight of the solids by weight of the sludge. So to calculate the weight of the sludge, what we'll do is we will divide 1200 by the percentage. So in that, by if you see weight of the solids divided by weight of the sludge, weight of the solids divided by weight of solids by weight of sludge will give us weight of the sludge, and that value is coming to 8642 kilograms of sludge. Although I think the answer has been given provided in the range of 8700 to 750. I'm getting this answer. If anyone of you have done, Sangamitra, Mujahid, or Alex?
Actually, in question number 12, weight of solid I got 1221 kg per day.
Okay.
So actually you got 1210, I got 1221. Then
Okay.
accordingly in question number 13, I got 8721.42.
1221 divided by 0.4. Okay. Can you just help me with I mean your calculation? How have you done the calculation? Is it something similar to this, or did you do it differently?
No, same thing I have done. But the thing is, actually now I lost my calculator. I'm doing in my mobile. So
Oh,
in
okay.
calculator, you might have set after decimal point something you have set. So
Okay,
in that,
okay.
some range difference will come, whether you have set 3 digits or 9 digits after decimal point. So accordingly,
Maybe. Okay. So I mean, the method, if the method is correct, maybe calculations small here and there, the values might change. So
yes,
this is how the problem is done. I'll also just go through the calculator issue and just reset it and try doing once again. And okay, so here is the 14th question. Treated water from a 15 million liter per day filtration unit outlet with TDS 850 milligram per liter. It is further treated by a uh, UF followed by RO. The UF is permeating 100% water, which means the UF is treating 100% of water which is coming in inside and removing 25% of the solids from it. And then RO, the water is going into the RO. In RO, 96% of the TDS is removed. 77% of the water is only being treated. The question, two questions have been asked. One is the TDS level in the RO treated water and the TDS level in the reject. Again, the TDS level in the reject, I'm getting some weird answers, so I didn't put it in the slide. Although I'll verify with the calculation with you guys. So for calculating the TDS removal, TD in the 14th question, TDS level in RO treated water. This is how I've done the calculation here. TDS removal is said as 25% in the ultra filtration unit. They have said that 25% of the TDS is removed. So we know that the TDS in the permeate or the treated water is going to be 75% of the TDS that had come inside. So TDS that had come inside is 850 milligram per liter. So when you multiply it with 0.75, you will get 637.5 milligrams per liter. Now, the ultrafiltration unit is treating 100% of the water which is coming inside. So, the inflow was 150 million liters per day. So, the inflow in the UF also will be 150 million liters per day. Now, let's go to the RO. Water is now going from the UF to the RO. RO is said to treat only 70, is only treating 77%, releasing only 77% of the water as treated water. So, when you multiply 0.77 into 150, you will get 115.5 million liters per day. Also, they have said that RO is removing only 96% of the TDS. So, the TDS in the RO permeate or the RO treated water is going to be 4%. So, when you multiply 4% with this TDS of the UF, this is actually the final TDS, you will get 25.5 milligram per liter. Is this somewhat the same answer that you're getting, or are you getting a different one? Sangamitra, were you able to do this question?
no, I could not do it. It was wrong in my case.
Okay. Okay, so this is the answer that I'm getting for the 14th question. Again, there's a problem with the 15th question. The answer I am getting is not in the range. I have done the steps, but I actually forgot to 33.1. 33.1 is the answer for what, Mujahid? The TDS RO removal. Is that what you're getting? Could you just clarify this 33.1 and 14 are answers for what? Question number 14. Okay, maybe you can just verify with this method and just see, compare it with yours, and then either we can wait for the assignment questions, assignment answers to come up, or we can discuss it in the next class, or and if you're not able to figure out a solution, we'll put it in the discussion forum definitely. 15th question, like I said, I got RO treated. I took 75. Okay. Okay. And although I'm not really clear what you're trying to say here, I do one thing, just verify with this solution that I've put here, and let me know if there's any discrepancy in it. And if in case such anything is there, we can discuss it in the next problem solving session once again. Meanwhile, I'll also post the answer for 15, whatever I'm getting. And we'll also, hopefully, they'll be posting the assignment solution, then we can cross verify with that and clear out where we are going wrong and everything. So we'll discuss about this last assignment 7, 14th and 15th question once more, maybe in the next problem solving session. I think today that will be it. If you have any doubt regarding today's session, you can stay back, or we'll wind up the session for today.
Okay, next time we can discuss. Actually, I'll try to solve also these two questions. And
Okay, okay, okay. So Alex and Mujahid, if you don't have any doubts, we can wind up the session. We'll meet next week. Thank you for attending the class. Thank you, Alex and Mujahid. Have a nice weekend.